This is a video on energy. Energy is defined as the ability to move matter or produce change. Also the ability to do work. We don't really know what work is yet, so we'll save that for a little bit later. Producing change is more of a chemistry definition for energy. In physics, we mostly refer to energy as the ability to move matter. Units in the metric system for energy are the joule. Joule is equal to a Newton times a meter. A couple different kinds of energy that show up in physics. One of them is potential energy. Potential energy is just stored energy. And if we're going to store it based on height, we call that gravitational potential energy. GPE is equal to the mass times acceleration due to gravity times the height of the object. And we usually just shorten up GPE and call it PE. And the equation again is PE equals mgh. Again, the units are going to be joules. When you look at the mass times acceleration due to gravity, that's a weight. Units for weight are newtons, and the units for height are meters. So we end up with a Newton times a meter, which we shorten up to call a joule. All of these are examples of potential energy. All of them are objects that have mass and are above the ground. None of them are moving yet. Eventually the kids on the carnival ride will move, but right now they only have potential energy. Same is true of the bungee jumper and the diver on the platform. Anything that is suspended or sitting on a shelf above the ground is going to have potential energy. Objects in trees, the gentleman sitting on the pole, even the sledgehammer that's held above your head before you let it go has potential energy. They all have the ability to do work at a later point. There are other kinds of potential energy other than gravitational potential energy. The other big one is elastic potential energy. That's energy that's stored in anything that will stretch or compress, like a spring or a rubber band. This math gets a little more complicated, so we're going to save that for a future course. But just know that there are other ways to store energy other than just based on height. Learning target number 1 is to be able to use that equation, P equals mgh, to calculate gravitational potential energy in joules. Here's an example of how to do that. If we want to calculate potential energy, we need to know the mass, we need to know the height, and we need to know the equation. So we have potential energy is equal to mass, which is 20 kilograms. Now the most common mistake that people make in calculating potential energy is they forget to multiply by G. G doesn't usually show up in the problem anywhere. It's something that they're assuming that you know. And G is again equal to 9.8 meters per second squared. That's the acceleration due to gravity here on Earth. So it's 20 kilograms times 9.8 meters per second squared times the height of 4 meters. When you do the math, you end up with 784. Your units are kilogram times meter per second squared times a meter. And a kilogram times a meter per second squared is a Newton. So again, we have Newton meters, and that is the same thing as a joule. So our final answer is potential energy is equal to 784 joules. Kinetic energy is the other main type of energy that we deal with in physics. Kinetic energy is the energy of an object because of its motion. And again, there's an equation for calculating kinetic energy, and the equation is 1/2 mass times velocity squared. Because the velocity is squared, kinetic energy depends a lot more on velocity than it does on mass. And again, we're going to have metric units of a joule, which again is the Newton meter. All of these are examples of kinetic energy. All of them are moving. And the other thing that they all have in common is that they are all on the ground. Learning target number 2 is to be able to use the kinetic energy equation to calculate kinetic energy in joules. Here's an example for kinetic energy. We're given a mass of 10 kilograms, a velocity of 3 meters per second, and we know our equation is 1/2 mv squared. So we take 1/2 times the mass, which is 10 kilograms, multiply it by 3 meters per second. And again, here's where people make the biggest mistake on kinetic energy. They forget to square things. Make sure you remember to square the velocity. And we are only squaring the velocity. We don't square the 1/2 or the 10 kilograms. We just square the 3 meters per second. So we end up with 1/2 times 10 kilograms times 9 meters squared per second squared. 3 squared is 9, and you also have to square the units. When you do the math, 1/2 times 10 is 5, 5 times 9 is 45, and our units are a kilogram times a meter per second squared, and we have an extra meter left over. So once again, we end up with 45 Newton meters, and a Newton meter is just a joule. So the kinetic energy in this example is 45 joules. Here's another example. We have Shawn Johnson, silver medalist in the floor routine, and a sumo wrestler. We want to know which one of their floor routines has the most kinetic energy. So if you do the math for the sumo wrestler, 1/2 times 120 times 3 meters per second, and again square that, we end up with kinetic energy of 540 joules. Now if you compare that to Shawn Johnson, 1/2 times 40 times 12 meters per second, again squared, we end up with kinetic energy of 2,800 joules. So you can see that Shawn has about 5 times more kinetic energy because she has a much larger velocity. So again, velocity matters a lot more in calculating kinetic energy than mass does. Here's some examples of both kinetic and potential energy. In each one of these examples, the object is both moving and above the ground. The plane is above the ground and moving. The dolphins are above the ground and moving. The football is above the ground and moving. And then the trampoline, the swing, the roller coaster are all examples of both potential and kinetic energy. So learning target number 3 is to know the difference between kinetic and potential energy given different situations or examples. So what type of energy would a bird sitting on a perch be? And that is just potential. It's not moving. Here's an example of a child on a trampoline. Has both potential and kinetic, above the ground and moving. Basketball player running down the court is just moving. It's on the ground, so it has 0 height. The lion on the ledge is not moving, so it doesn't have any kinetic energy. It's all potential. Flying through the air on the slam dunk, you are above the ground and also moving, so both potential and kinetic. Toy sitting on a shelf, not moving, is just potential energy. The ball rolling down an alley is just moving. It is on the ground, so the height is 0. So no potential, all kinetic. Going down a slide is a combination of potential and kinetic. You are above ground 0 and you are moving. How about this last one? This last one is a gnome sitting in the grass. And this is an example of no energy. It's not moving and it is on the ground. Here's a mystery machine. Mystery machine is moving, so that is only kinetic energy.